Hello, my sweet physics students. Here are some notes on rotation. Recall from Monday, yesterday, that we have arc length is the radius of a circle times the angle in radians. And for some constant radius, we can take the time derivative and find that the tangential velocity is the radius times the angular speed, omega. Take the time derivative again, and we find that tangential acceleration for an object moving around in a circle is the radius of that circle times the angular acceleration. So we also wrote down some kinematics equations for rotational motion. Directly analogous to what we did at the very beginning of the year. If we have constant angular acceleration, we can use the definition and do an integral, and we get that the angular speed as a function of time is the angular acceleration times time plus the initial angular speed. Integrating again, we find that the angle as a function of time, the angular position as a function of time, is 1/2 the angular acceleration times time squared plus the initial angular speed times time plus the initial angular position. And we can eliminate time from the equation, again, analogous to what we did in our initial unit on kinematics, to find that the final angular speed squared is the initial angular speed squared plus twice the angular acceleration times the change in the angular position. And by using these relationships, we can rewrite the centripetal acceleration as we did yesterday to get the radius times the angular speed squared. Page 2. If we consider the cause of rotation, we get Newton's second laws for rotation. Now the cause, in order to rotate something, we call that the torque. The official definition is as a vector product or a cross product. The torque is defined as R cross F, where R is the distance from an axis of rotation to a place where a force is applied. And of course F is the force. Now to find the magnitude, we can look at this a couple different ways. A definition says that it's the radius, the distance from an axis of rotation to a place where the force is applied, times the force, times the sine of the angle between them when you line them up tail to tail. This is the same thing as the perpendicular distance from the axis to the line of action for the force, times the force, or this distance from the axis of rotation, r, times the perpendicular component of the force. So take a look at the diagrams. That's how you find magnitude for the torque. To find the direction, we use the right-hand rule, which I'll need to go over with you in class, or page 3. The torque can be calculated using a determinant. Now, it's not officially a determinant, but it is a good mnemonic. And you can look at the notation on page 3 here. This will give you a component form of the vector product. So it gives you a vector as a result. So torque is the cause of angular acceleration. By considering kinetic energy, we can define a new term, which will be analogous to mass, namely rotational inertia, or this moment of inertia. For a rigid object, that means that all the particles stay relationally the same distance from one another, fixed in space, as they rotate about some axis. Well, then the angular speed would be constant. And so here on page 4, we can rewrite the kinetic energy for a system of particles. And factoring some things out that are constant, factor out the 1/2 from the summation, and factor out this constant angular speed squared, what's left we're going to define as the rotational inertia. So note that if there's more mass further from the axis of rotation, that makes it harder to change the angular velocity, harder to accelerate with an angular acceleration. And we define the kinetic energy of rotation as 1/2 this rotational inertia or moment of inertia times the angular speed squared. And then we can write Newton's second law for rotation. Torque is the rotational inertia times the angular acceleration. Now, this is for symmetric objects, so we'll have a better definition for torque, but this is analogous to that Newton's second law for translational motion. Similarly, we can rewrite power. So power is the torque times the angular velocity. Just like for translational motion, we derived that power was the force times the linear velocity. So next, we're going to work on calculating this rotational inertia or moment of inertia for a few objects which are geometrically simple. Page 5, our first one, we'll do a uniform rod of length L and mass M. Rotated about one end of the rod. So take a look at the diagram. We define that linear mass density is mass per unit length, or in this case, lambda will be m over L. We're going to integrate r squared dm. Now in this case, the position of those little chunks of mass, I set up an x-axis. So we have the integral as x goes from 0 to L of x squared dm. And dm is lambda dx. So performing the integral, we find that this moment of inertia for a rod of length L and mass m is 1/3 the mass times the length squared. What if we rotate about the center of the rod? You can look through the calculations, similar integral, but this time we're integrating from negative L over 2 to L over 2, and you get 1/12 the mass times the length squared. A smaller number. It's easier to rotate about the center than about the end because the mass is more concentrated toward that axis of rotation. So in general, for lovely rotationally symmetric rigid bodies, the rotational inertia is some constant times the mass and times some length squared. Now it might be r squared or L squared. We can use different variables depending upon what the geometry is. So if we have a disk, for example, we'll use sigma because we have a surface, an area that we're going to integrate over, and we end up finding that the rotational inertia, as we integrate from 0 to r for a disk of radius r, and as the angle goes from 0 to 2 pi, we find that the rotational inertia is 1/2 the mass times the radius squared. Again, some constant times the mass of the disk times the radius squared. I'd like you to think about doing calculations for a cylinder or a ring instead of a disk, and see if you can't almost intuitively come up with these moments of inertia for those two objects, a cylinder and a ring. The final thing, and I'll do this separately because it'll take a little while, is to find the moment of inertia for a sphere or a spherical shell, and I'll use spherical coordinates. That's why it'll take a little while, because I'll have to explain that as well. Now, Last thing for this set of notes, the list of moments of inertia can expand rapidly when we think about all the various axes of rotation. And to accommodate our calculations, we'll use the parallel axis theorem, which I'm not going to prove here, but the rotational inertia about some other axis other than what goes through the center of mass is the rotational inertia for the center of mass plus the mass times the distance from the center of mass to that axis of rotation. It's parallel squared. So I equals I center of mass plus the mass times r squared, as you can see written down here. So for a planar mass distribution, we can also come up with a perpendicular axis theorem. And that says, again, I'm not proving it, but I, the rotational inertia about an axis z that would be perpendicular to both x and y, is ix plus iy. And I show an example here of how to find the rotational inertia for a hoop about an axis that is in the plane of the hoop. So in the picture, it's an axis like y or x, and rotating the hoop about that axis instead of about the center, through the center of the plane. All right, that's it for now. Let's get to work and solve some problems.